Okay, so it's an honor, pleasure to introduce Laura Doval, who she will be our speaker today. And Laura, you have a very interesting and long story. I mean that you are from Argentina, which is from the American continent, but far from the US. So, and then Laura got his PhD or graduated in the Northwestern University, and she is at the Columbia Business School at the moment, the economics division. And even if, Laura, you're very young, but you have very nice papers and in very prestigious journals. And she's already in the editorial board of the Theoretical Economics and Journal of European Economic Association and Economic Theory and Economic Theory Bulletin. So she's very in the middle of the business already. Many fellowship grants, awards, and so on. So really already very, very heavyweight researcher. And today, what we would like to hopefully we will learn from her is persuasion and warfare. So Laura, the screen is yours.
Well, thank you so much, and especially for such a kind introduction. I feel like your beliefs will drop very suddenly with the talk, but I really appreciate the kind words, and also the thank you for having me here. So this is joint work with Alex Mollin, and I think that it's going to be a bit of a change from it will be a more conceptual paper. I think that some of what I've seen people present in this series. So a little bit of the motivation for this paper is to try to think about the role of information as a tool to guide policy choices in high stakes domains. And if I prompt you with this term, you would probably think about anything that you've learned recently about the role of algorithmic scores and recommendations in decision making. So there's a lot of things written about how algorithms are used to determine who gets bail, who gets a job, what kind of health treatments you're going to receive, what kind of education you're going to get, and whether you get a loan or not. But I'm a little bit old school, and I like to remind myself that this is the role of information as a policy tool to guide decision making is by no means confined to the machine learning economy. We've used coarse measures like the FICO score to determine who gets a loan and the price that they should pay for a loan, and the role of testing and grade disclosure policies in determining which students go to which colleges and which college students get what job or which MBA students get a job have been is something that we're very familiar with. But I do think that all this buzz around algorithmic recommendations has made us very much aware that something as innocuous as information can have very important welfare impacts, and this welfare impact can be very heterogeneous across different agents in the population. And that prompts the question of, well, if this policy in particular has a certain welfare impact, how do I think of changing the policy, or what policies would have good properties? But for that, we would need to be able to have a framework that allows us to talk about the trade-offs the welfare trade-offs from moving from one policy to the next. And basically, this is what we want to do with Alex. We want to provide a framework that will allow us to study the welfare impact of information policies in a population of heterogeneous individuals. The exercise will be a little bit like when we characterize what's incentive compatible in mechanism design. So we're going to characterize everything that is feasible given information. And now, given that, we're going to be able to, given our social welfare function, then think about what information policies to choose. So more formally, we're going to be looking at a simple model where there's a unimodal population with characteristics in a finite type space, theta 1 through theta n. And we're going to have a full support distribution mu0 that is going to describe the frequency of individuals with different characteristics in the population. our main primitive is what we're going to call the welfare function. And the welfare function is going to give us the welfare of individuals with a given characteristic as a function of the beliefs that an unmodeled outside observer has about the distribution of characteristics in the population. We're going to follow like an information design approach where information policies are going to be information structures. And I probably don't need to tell this to this crowd, but just for common knowledge, we're going to think of information structures as a set of labels and as a set of conditional probability distributions that say for each characteristic, the distribution of signals. And we're going to assume that the outside observer will observe the signal realization, but not the individual's characteristic. So the outside observer will be basically be a black box for us to perform base rule. So let me pause. Is there a question? Ah, by the way, I should say that, please, if there's questions. Oh, yes.
About welfare functions. So
yes,
set of distributions of theta is the common prior. What is that?
So theta is theta is just the characteristics of the individual. So for instance, it could be in the bail application, the probability that an individual will again commit a crime if I give them bail, or if you're thinking about a job market, it could be the ability of different individuals.
Mm-hmm.
And then
of everyone. That's the complete profile of their types, right?
So it's going to be it's going to be a it's going to be a unit population with characteristics. So there's not going to be a profile of types. You could think of like you have a unit interval, and different intervals in the unit interval have different characteristics. So we have like a certain mu 0 theta 1 will have characteristic theta 1, mu 0 theta 2 will have characteristic theta 2. So we're not going to be thinking about a profile of types, but yes, I'm going to be thinking about a profile of payoffs, one for each type. That's going to be the next slide.
When I want to see the payoff of a certain type, the type is the second element in this tuple, in this Cartesian product. Yes, that's the
yes.
And the first element is what is the first element?
So the first element, is the belief, is a distribution over characteristics in the population. So one way to think about it is think of Holmstrom's model. So theta would be the abilities of the individuals.
Mm-hmm.
Mu is a belief over the ability distribution in the population. And W is expected value. So W will be type independent. It will be the expected value of the ability profile. So it will be, and why would you care about this? Because in Holmstrom's model, that's the payoff, because the market pays you your expected productivity.
Mm-hmm. The prior mu is the common knowledge, right?
So the prior mu naught is going to be common knowledge.
Mm-hmm. Okay, thank you.
But this could be different from the prior.
And what is the motivation for that? That the first argument of W may not be mu naught? Why would that be?
Thank you. So because you could imagine, so that the mu naught could be an argument for that function. You could imagine not providing information about the individual's characteristics in the population, and then everyone gets, each individual will get a payoff W mu naught of theta. But you could imagine that now you want to say, disclose going back to the Holmstrom example, whether an individual's ability is above or below a certain threshold. And therefore, some types will have, when you evaluate their welfare under that, some characteristics will be assigned to some beliefs and some characteristics will be assigned to other beliefs. as long as we satisfy that the beliefs average to the prior, that will be allowed. So you might want to think about inducing different beliefs to induce different welfares in the population.
Thank you.
Maybe, so I think this is a good segue to go to the next slide. If you give me a welfare function together with an information structure, I can now talk about a welfare profile, which is for each characteristic, the welfare of individuals of that characteristic under that information structure. So theta will enter twice in this calculation. One is to say the welfare of who we are evaluating, but also it enters here to determine the conditional probability distribution of the signals. And basically, so this is expected in the welfare of individuals of type theta under the information structure, and we're going to distinguish welfare profiles that are induced by information structures by calling them base welfare profiles. So when I say a base welfare profile, I mean that there's an information structure such that the payoff of individuals of a given characteristic is their expected welfare under that information structure. And our object of study, our objects of study is going to be the base welfare set, which is the set of all base welfare profiles. So it is a set of all vectors in Rm that can be induced by some information structure. And basically, this is the main object that we define in the paper, and all our results are going to be characterizations and tools to analyze this set. So going back to the motivation, so the base welfare set is the utility possibility set in an economy where your allocations are information structures. And you would think that this is so it will describe everything that is feasible. And then you have your social welfare function, and then you pick from this set which welfare profile you want to induce, and therefore that will determine the policy that you will induce. And we think that this is the key object to study the welfare implications of different information policies, like when we think about market segmentations or grading policies or recommendation systems. Now, let me flag 3 things about what we're doing and what we are not doing, and in terms of positioning relative to the literature, because we are going to allow for all information structures. We're going to sort of provide a complementary view to the algorithmic fairness literature. Usually the algorithmic fairness literature presumes properties the policy has to satisfy. Instead, that literature, what it does is it remains agnostic about the payoffs of the population or even the social welfare function of the agents, whereas we're going to follow more an economics approach, where we're going to say you understand the payoffs of the agent and you know as a planner what trade-offs you have in terms of the welfare of the agents, but we're going to allow for a richer class of information structures. It also complements the literature on information design. So you will see that there will be a lot of the toolkit from Oman and Maschler that is going to be used in this paper, but basically usually that toolkit is used to characterize the maximum ex-ante welfare, so the average under the prior mu naught of the profiles in that set, whereas we will be interested in understanding the cross-section of the payoffs. So that will be our complementary view relative to that literature. Now, things that we have little to say about. One is, even though I mentioned this algorithmic fairness literature and algorithmic recommendations, there's one issue that literature points out, which is the role of data that is biased, because I'm getting recommendations that are based on data that are used in past actions. We won't have this. So here the model is completely static. There's 2 places where you might think that you could incorporate some of this bias. One is in the prior. So in a couple of slides from now, it will become very evident that mu naught does not need to be the objective distribution of types in the population. It's only the distribution in the eyes of the outside observer. And therefore, you could think that all the biases that come from past data can be built into the prior. And the other place where you could think of incorporating biases in decision-making is in the welfare function. So we're taking this reduced form approach where we think about the welfare function as a function of beliefs and types, but you could imagine a more primitive version of this where you're modeling why the agents care about the beliefs of the outside observer, and you could think of the welfare function as the composition of whatever the outside observer does given their information with how the agents in the population care about this. So this is another way that our model allows for this bias. The other thing is that we're going to it's important for us that there's a single outside observer. So if you wanted to think about this model as after the signal realization, there's going to be some strategic interaction between multiple outside observers, we have the limitation that we're only doing public signals. So if you, so we're not capturing the full extent of what you might be able to do with information policies if you had multiple outside observers. So I will go through the literature a lot. You will see that in a sense, the paper, what it does is it also provides like a new way to interpret results in the literature. So I will mention a bunch of papers as I go along. Something that I want to do, but I think it's kind of important. You might not be interested in thinking about welfare possibilities through information, but the base welfare set is also a way to encode incentive constraints when information designers have private information. So you could think that when you have an informed principal like in Perez-Richet or Kessler and Skreta, or the principal designs an experiment, but he gets information from a privately informed agent, like in my work with Vasiliki, you're designing an information structure subject to incentive constraints. And these constraints are determined by the welfare that the different the different types in the economy are going to get given the experiment. So the base welfare set is also a way to encode the incentive compatibility constraints. And there is, so in a sense, you could think of what we're doing as a tool for information design, and we have a previous version of the paper where we did this, but we decided not to try to tell two stories in one paper, and we thought that we wanted to focus on this one. Questions? Okay, so what I'm going to do, I'm going to give you a belief-based characterization of the base welfare set, and I'm going to do this first in general, and then I'm going to specialize to a particular class of welfare functions to try to distill some things that I don't think we knew before. And then I'm going to focus on the Pareto frontier of the base welfare set that, given the applications that we have in mind, it seems like the focal point if you're thinking about what a social planner would choose in this set. I don't think I will get to section 3 of the talk, so let me tell you what I'm not going to tell you later on. Given the applications that we have in mind, it would be natural to think that we cannot disclose all kinds of information about the individuals in the population. So our information policies allow all kinds of disclosure, and you might say, well, look, there's some things that are protected by the law and you cannot disclose. So there's some limits on the data that you can provide. We have a section, we show in the paper how to extend this. And in particular, we show that once you take the point of view of you are characterizing everything that's feasible, and then you're going to choose from that, then some of the ideas that show up in algorithmic fairness about restricting the set of information structures actually can be welfare reducing. And hopefully I'll have some time to elaborate on this at the end, but otherwise I'm also happy to talk about it offline. So what's the goal then? We want to characterize what welfare profiles are consistent with information, and basically recall that each element of this vector is, I didn't know that. So I don't know if that happened for you too. I don't know that that's new thing about the mouse. So basically, each element of this vector is a conditional. Is a value of the welfare, is a conditional expectation of the welfare function given the information structure. So this is, in a sense, an apparent challenge in trying to use a belief-based approach, because usually the tools of Ullmann, Maschler, and then Kamenitz and Genskow apply to unconditional posterior distributions as opposed to conditional ones. And you might say, well, this is only it's a superficial distinction, but unconditional and conditional posterior distributions are different. So unconditionally, beliefs follow a martingale. So they are going to return to the mean, they're going to average the prior. But actually, if you think about conditional expectations, what happens is that they will satisfy a property that we call they drift towards the truth. So what do I mean by this? If you fix a characteristic in the population and you give me an information structure pi, you could think for each realized belief, posterior belief, to calculate the likelihood ratio between that belief and the prior. And then taking the expectation over this. So if I didn't have the conditioning here, this is a complicated version of writing the martingale property. This should add up to 1, but you can show that this is always greater or equal to 1. So this is in a paper by Wood, a very old paper, and then Francis and Krebs also show this using the properties of the Kullback-Leibler divergence. And we're going to recuperate also this property through our characterization. But this means that we can do one of two things. We can either characterize conditional posterior distributions, and this is actually where we started. And then we realized that for our particular application, this was not the right way to go. But there's more contemporaneous papers that do find nice applications of the characterization of conditional posterior distributions. What we're going to do instead is we're going to find a way of incorporating this drift into the welfare function so that we can use then the martingale property of unconditional posterior distributions. Elon.
Laura?
Yes.
So it seems to me that there is a relation between what you do here and the recent paper by Omer Tamuz and Itai Arieli and Yakov Babichenko. So are you aware of this relation, or is it not related at all and it's all in my mind?
So I know of that paper. But for a long time so for instance, this paper, in this paper, so Omer's paper with Itai and Yakov and Fedor, they're looking at the projection, at some projected version of the set of conditional posterior distributions. In the new paper, and I think Omer is not in that one. I think that's just Itai, Fedor, and Yakov. They instead of looking at the projected set, they look at the domain and at the original set, and this is the paper where they actually have the characterization. But yeah, so I don't know if there's like an immediate connection to be done, but I would have to, maybe I should go and check the paper again. Did you have any thought maybe I should ask you if you had any thought in mind?
No, it just occurred to me that those questions are related, that's it.
Yes. Gleb?
Could you please go one slide back first?
Yes. Here, this?
Yes. So I'm just trying to unfold that last formula. So what you write in the last formula is basically that for any inside how do you call this base welfare set, the welfare is always the expected welfare given the. I'm basically trying to unfold the formula. Maybe you could just explain it once more. It would be easier.
Yes. So so basically we're fixing a type of the agent, and we're asking what's the expected value of W under the information structure.
Mhm.
So and therefore, because I've already fixed theta,
Mhm.
I'm only using the conditional distribution of signals. And this is the thing that maybe I brushed over too quickly. This is the belief of the outside observer conditional on signal S, but before seeing theta. So the agent knows theta, the outside observer does not know theta. So from the point of view of the agent, the belief of the outside observer before seeing S is random.
Mhm.
And therefore, that's why even for the agent, there is some uncertainty about what payoff they will get.
Mhm.
And if you give me a couple of slides, I will return to this idea, because this is a little bit like a second order expectation.
Okay.
So the agent knows theta, the outside observer does not know. The agent might ask himself, what is the probability that the outside observer has different beliefs?
Mhm. Mhm. Mhm.
And because that's uncertain, now you have the possibility of like calculating this expected payoff. Does that help?
Yeah.
Okay.
Thanks.
Let me know. I have another way of thinking about it if it helps, and you can let me know if.
Okay.
So basically, now I'm going to just show you a slide with algebra, but basically I want to make very precise what it means that we're going to incorporate this truth drift into the welfare function. So we want to calculate the expected welfare of individuals of type theta under the information structure. So I can decompose this as thinking first on what beliefs the information structure is going to induce, and then the signals that lead to this belief. And then what we can do is multiply and divide both by the prior and by the unconditional probability under the prior of observing signal S. And once we do that, what we get here is, this is a belief that the outside observer has about the agent's type, mu of theta, under the information structure. So basically what we can write now is that the expected value of the welfare function conditional of theta under the information structure is this expectation now with the unconditional distribution of signals of the welfare function times the thing that I told you that in general does not average to one conditional of theta. And we're going to call this an adjusted version of the welfare function W hat. We call it the truth adjusted welfare function. And basically the algebra that we just did says that for each information structure and each type theta, if I wanted to evaluate the welfare of individuals of type theta under the under the information structure pi, I can instead take the unconditional distribution of signals of information structure pi and calculate the expectation of function W hat mu theta under that information structure. So basically, what this will allow us, this transformation to the welfare function does is simply a change of measures. It will allow us to combine inside the utility function both the preferences of the agents, but also the budget constraint. So you can think that individuals of characteristic theta, they have a budget which is their proportion in the population. they can distribute this into different signals that they are going, into different beliefs that they're going to be mapped to. And basically this adjustment is going to ensure that these beliefs are allocated in a feasible way. And this transformation, we're not the first ones to observe it. The earliest reference we have is a paper, but and if you have more, please let us know, because this has been we always like get something even older than this. But Laclau and Renaud have this paper where they talk about public persuasion, and they use this transformation to be able to link the beliefs of all the agents. It shows up in Alonso and Camara and Rosar. Vasiliki and I use it multiple times in our work. And so it's Quigler, Walder, Liebgover, and I'm pretty sure that someone in the audience might know of more. But for us, this is going to be a way to be able to rely on the usual Oman Maschler toolkit to do the characterization. So let me give you very quickly an example, just to give you a sense of the difference between the welfare function and the truth-adjusted welfare function. Let's think that we have an online marketplace that has two types of sellers, low quality and high quality. And the consumers believe that both types are equally likely, but they would like, all else equal, to buy from high quality sellers. So we're going to model this in a very reduced form way. We're going to say, well, both sellers have the same welfare. They get purchase with probability 1 if the beliefs are high enough. The consumer will flip a coin if they are sort of undecided whether we have a low quality or high quality seller. Sorry, I should have said, I'm going to now abuse notation, and this will be just the probability of the high quality sellers. And then no one purchases if you think that the seller is low quality. So you could think that when you're designing a recommendation system to guide consumers in the platform, basically you're picking elements in our set. So in this example, if you think about
one clarification question. So
yeah,
the belief of a consumer is the same for each seller, right? You write mu0 of theta is half,
yes,
but of which theta? Of theta 1, of theta 2?
Yeah, so that's why I said I should have said, so now I'm abusing notation. Mu is the probability of that the consumer believes, is a probability that the consumer is facing theta 2.
Again, please.
So I'm abusing notation here, you're absolutely right. Mu now it's not a distribution, it's a number between 0 and 1, and it's indexing the probability that the consumer, that the seller is of type theta 2.
So everything basically you're just without also generality, you're concentrating on seller 2, right?
But this is a welfare of both of them.
Okay,
this is a welfare of both of them. But I can, without loss of generality, write the utility function just as a function of the belief of seller 2.
Yeah, okay, thanks.
Thanks, sorry about that. So the welfare function in this example is very standard. It's like the judge example in Kamenitsa and Genska with one more step. But if you calculate now the truth-adjusted version of the welfare function, let's start with the low-quality sellers, it looks quite different. So one simple thing that you can note is that both sellers would love to get purchases with probability 1, but it's impossible for a seller of low quality to be represented in a belief where the consumer assigns probability 1 to the seller being of high quality. And this is why the payoff here is 0, even though exposed, you would get a payoff of 1. So basically, what and similarly here, this bit is also decreasing because the probability of being in the middle trench, conditional on being of type theta 1, is smaller and smaller. On the flip side of this is that the high quality sellers have a bump on their utility when we look at the truth-adjusted welfare function, because they can be overly represented relative to the prior in these higher beliefs where the purchase happens with probability 1. So in a sense, even though exposed, both sellers have the same utility function, when we incorporate their budget constraint via base plausibility, we are going to get this sort of distorted version of the welfare function that will allow us to also capture what kinds of information structures each of them would like. Now, this claim that I showed you already says that if you only care about the welfare of one of the types in the population, then you can use a truth-adjusted welfare function and everything we know from Aumann-Maschler to characterize individually feasible welfare levels. Because that claim that I showed you basically says that if you only are interested in the welfare of agents of type I, then I can represent the feasible welfare levels of type I by looking at distributions over posteriors that average to the prior and asking myself which are the W of i's that correspond to the expected value under tau of the adjusted welfare function. And that is basically this interval. The convexification of the adjusted welfare function at the prior all the way to its concavification. So if we go back to the example that I just showed you, you can think basically what we're doing is we're taking the convex hull of the graph of the truth-adjusted welfare function. We're looking at its section at the prior, and that is the interval that we're interested in. You can do the same for the high quality sellers, and you could have done the same also in the standard unconditional setting. Now, hopefully there's something else to tell you, like if the answer was that simple, the paper ends here, but the issue is that when you're trying to think about what is feasible for the population, you cannot just take the products of this set. So one easy way to see it is that what the sellers of type 1 would like to do is to get a split between 1/3 and 2/3. Whereas the high quality sellers, they would like some separation. They would like to be sufficiently separated that at least the consumer is thinks that their probability is at least 2/3, and then they would like to remove the low quality sellers from there as well. So how are we going to get the profiles that are jointly feasible? We're going to think about the welfare adjusted function as a vector. So we're going to think of it as a vector that assigns for each belief a vector in Rn. And once you do that, you're going to get the characterization. So basically, the base welfare set is going to correspond to the following. We're going to calculate the graph of this vector valued function. We're going to take its convex hull, and then we're going to look at the section at the prior of this convex hull. And that is going to be the set of welfare profiles that are induced by some information structure. And this will allow us to capture everything that is jointly feasible. So you could think of this as a vector valued version of Cummins and Genska, Rush and Seagal, of course also Aumann and Maschler. Johannes Hearn mentioned to us that actually Aumann and Maschler have a vector valued version of the CAV theorem, so used for very different purposes. But these are all morally related results. So if we go to the example, so I now am plotting the welfare function in a weird way. So I'm putting the beliefs in the vertical axis. So that's why we're getting the solid bars here. And we can take the truth-adjusted welfare function. And what the theorem says is that we should look at the convex hull of the graph of that function, and then we're going to get the cut at the prior, and then we can project that down. So basically, this is what it looks like. This is what the base welfare set looks like in the marketplace example. I'm singling out here the full disclosure profile where we reveal the types, and therefore everyone buys from high quality sellers, no one buys from low quality sellers. The no disclosure profile is everyone flips a coin because at the prior, everyone is equally likely. So we already saw this in the truth adjusted welfare function. Even though the welfare functions of the sellers are equal, exposed, at the interim respect to beliefs, they are asymmetric, and therefore the set is asymmetric. The only point that is on the 45-degree line is the no disclosure profile. We already talked that we cannot simultaneously maximize low and high quality seller profits, but now we can visualize it. And we have all these horizontal and vertical planes that shows us that we can distribute welfare, sometimes increasing the low quality sellers without hurting the high quality sellers, but we can also hurt the high quality sellers without doing anything to the low quality seller profits. So I'm not sure I will get to do, let me skip this because this is, especially for this audience, is a little bit of a triviality. You can use this characterization, for instance, to put bounds on the experiments, on the number of procedures that you will use at an optimal information structure. We're going to get more beliefs because you could think of this as an end-sender version of an information design problem. But let me, given time, I think I went very slow. Let me give you a special version of this characterization that I think is kind of it's kind of cute. So basically, let me think now about the case in which the welfare function is like in that Holmstrom example that I was mentioning at the beginning. It's the expectation of some random variable. I'm going to call that random variable rho. And I'm going to refer to rho as a reputation vector. So you can think of the welfare function now as individual's reputation. And then the base welfare profile will be a profile of expected reputations. And without loss, you can think that the types are ordered according to the values of rho. So why would we care about this setting? Well, in part it's because I'm going to be able to show you theorem 1 under a new light, but this is actually something that economics people use a lot, thinking about modeling reputation or image or career concerns as expectation of some random variable. But also, given the applications that we're interested in, usually this is also something that is used when thinking about giving treatments based on information. So if you were thinking about a decision maker or outside observer that is selecting a treatment to give to the agents in the population based on the prediction of an outcome of interest, how able they are, what's the probability that they're going to commit a crime again, what's their creditworthiness, then basically the decision is going to be based on the expected value of some random variable conditional on the information. So when you're thinking about the probability of assigning treatment, you want to see how high or low you can make these expected values. So in the linear model, information, the only thing it does is going to redistribute welfare across the agents, because base plausibility, or the marginal property of beliefs, will imply that if I take any welfare profile and I calculate its expected value, then it has to be the expected value, it's expected value under the prior distribution. It's going to be the expected value of the reputation vector. So basically what we're doing with information here is just deciding who gets what of this ex-ante reputation, this ex-ante value of reputation. And so if we go again, I'm missing an equal here. If we go again to theorem 1, and I wanted to say, well, what's a set of feasible welfare profiles under some information structure when the welfare function is linear, then I know that I need to look at type by type the expected value under some posterior distribution that averages out to the prior of this number. But of course, we want to do this jointly, so we can put this on matrix form. And this says that the welfare profile can be represented as a product of three terms: the reputation vector, a prior normalizing matrix, which is a diagonal that has in the II element 1 over the probability of theta I, and this matrix of likelihoods that come from the experiment. Now, this matrix has two special properties. One is that it is something that is called a completely positive matrix. So let me show you what that means. So a completely positive matrix is a matrix where I will have k vectors for some k, C1s through Ck. They are non-negative. And the matrix is obtained via the, so first I take the inner product, not the inner product, the cross product between these two vectors, and then I add them up. So if I show you for 1 second again this, so imagine this expectation being a sum, and the mu and mu tildes are the C's up to some normalization in that. So it's kind of easy to see that it satisfies the properties of the definition. These matrices show up a lot in convex optimization. One quick way to think about them is these are symmetric, positive semi-definite matrices that have positive elements. And this is their characterization if we had less than 4 types, but it is not, they are more general than this for n bigger than 5. And this number k that for us will represent how many beliefs you're going to induce in your information structure. This is something that this literature is sort of obsessed with. It's called the CP rank of a matrix, and there's lots of papers about how the CP rank relates to the rank of a matrix. But for us, it will represent the number of signals in that without loss you will induce in an experiment. The other thing that this matrix has is that its rows add up to the prior. So you could think of this as sneaking in this definition, the base plausibility constraint. And it turns out that that is all. So these properties are not only necessary, they are also sufficient. So in the linear case, if you give me a vector, it's going to be a base welfare profile if it's represented as a product of the diagonal matrix, a completely positive matrix whose rows average to the prior, and the reputation vector. So as I said, this condition is basically base plausibility coming through the back door. What does it mean? What is the complete positivity condition doing for us? It's going to be, and I'm going to be more formal about this in a second, it's going to be ensuring the balance of reputation flows across the types. So in a sense, you could think of whether you can convince a decision maker that type 1 is type 2 with probability 1. The complete positivity will be imposing the constraints that will say this is not feasible. So let me be more precise about this. If we normalize the complete positive matrix by the diagonal normalizing matrix, what we're going to get is a transition matrix of a reversible Markov chain. This is a right stochastic matrix and satisfies what is called detailed balance conditions, which basically says that the flow from I to J in terms of reputation has to be balanced, but has to be equal from J to I. So what this means is that this reversible Markov chain will have the prior as its invariant distribution. And this already tells you that you can think of then as any base welfare profile as taking the reputation vector raw and garbling it with this reversible Markov chain. And if you keep hitting it with the same matrix, what you're going to get is you're going to garble yourself all the way to no disclosure. So this is the mean reversion property. So you can think of starting from the full disclosure, the reputation vector, and then garbling all your self-weight into the no disclosure profile.
Laura, may I have a
Nicholas.
question?
Yes.
So, thank you. So when you consider this condition, which leads to this reversible Markov chain, practically what you say that you have a prior which is not focused on just some subsets of the types, but so those are very related that you can reach from any point to any point, right?
Mm-hmm.
So it means that there are no belief subspace. So belief subspaces, let me say, which are ignored. So each is the very same that each has a positive probability by a prior. Each type.
So the prior, we are assuming it is full support.
It has full support, okay. And it's
Yes.
enough for it. You need something more?
No,
Sure.
I don't think.
You
I don't
oh,
think so. But the only thing I want to say is that the complete positive matrix normalized by the prior is going to be a reversible Markov chain.
yeah.
And then the next question that you might have is, if you give me a reversible Markov chain whose invariant distribution is the prior, will this be another way of characterizing the base-Wolfert set in the linear case? And that is not true. So not as there's some reversible Markov chains that cannot be decomposed as completely positive matrices times the prior normalization.
And perhaps I asked too much. So can you give an intuition why it doesn't work in the other direction? So which are those matrices when you cannot do this?
So I think we should have an example of this in the paper, which we currently don't have. I think but I think that the main there's a symmetry that's inbuilt even before you normalize by the prior. So there's two things that there's the symmetry, and there's the I think the positivity. So the way the complete positive matrix is constructed also has implications for the IM vectors and the IM values that it doesn't recover all reversible Markov chains. But in a sense, like related to this, you actually gave me the correct segue. There's to this slide, and I think this is where I will probably have to then stop, is that reversible Markov chains actually feature prominently when people were studying higher order beliefs and expectations of higher order beliefs for a given information structure. And basically all these papers, they're thinking of a problem where you have Ann's expectation of a random variable, Bob's expectation of Ann's expectation conditional on Bob's information, and more levels. And I'm not going to try to embarrass myself trying to go through the third level. But if you think about what we are doing, we're doing a second order expectation. So think of Bob. Bob knows the theta, and Ann knows the realization of the information structure. That's a random variable. And now Bob is thinking, what is Ann's beliefs of over theta, given that I know theta? Now, this literature usually starts from an information structure, and then they say, look, you can obtain the sequences of higher order expectations by iteratively applying the transition matrix of a reversible Markov chain to the previous element in the sequence. And the thing is that because they start with an information structure, they have to end up with a reversible Markov chain. In a sense, what we are doing is we're going in the opposite direction. We are identifying which, if you wanted to just pick a reversible Markov chain and do the exercise in these papers, we are saying, well, there's some transition matrices that are originated by information, and there's some that are not. And the complete positivity is a property that is key. So given that I have, I guess I'm out of time. So I'm out of time, right? Because we started at 9.
We started 5 minutes later, so definitely
Okay,
you have
so
had 5 or 6 minutes to go.
okay, so let me very quickly mention something. So in the paper, the other thing we do is we think about the characterization of the Pareto frontier. And actually, as a consequence of this, we're basically characterizing the whole boundary of the set. But you could think that these are points of interest if you're thinking about a social planner choosing or society bargaining over information structures. And we're going to define the Pareto frontier using weak Pareto optimality. So we want that there's no strict improvements. And this is, if you think about the application that I showed you where I had this flat at the top, I want to be able to recover these points where I was not hurting the high quality sellers, but I'm improving the welfare of the low quality sellers. So basically what I will show you is that the Pareto frontier is basically can be characterized as the solution of some what we call supporting Bayesian persuasion problems. And as I said, this will give us also a characterization of the boundary. So if I pick a point in the Pareto frontier, we can, by the supporting hyperplane theorem, we will have that there is a direction lambda such that the point in the Pareto frontier solves that in that direction, W maximizes the product of lambda cross W over the base welfare set. And if we apply theorem 1, that means that we're maximizing over information structures, over base plausible posterior distributions, the product between lambda and the expectation of the truth adjusted welfare function. Now, because we're looking at non-negative directions, we can, without loss, call this a belief. And this is where I will tell you why the prior is only the belief of the outside observer and not necessarily the true distribution of the population. So you can think of this having two interpretations. You could think, well, this is the problem that a utilitarian planner that has Pareto weights on the agents will solve. Or you could think that because lambda is a belief, then this thing over here is the expectation under that belief of the profile, of the base welfare profile W. So when you take lambda equals to the prior, this maximization problem is the one that's the whole focus of Kamenitz-Angenschow. If you take a belief that's not the prior, you have the heterogeneous belief model of Alonso-Camara. So this is what makes very crystal clear that for us, mu naught is actually the belief of the outside observer. And you might think as a social planner that the outside observer has incorrect beliefs. They are still Bayesian, but they have wrong beliefs. And when you're solving your utilitarian welfare problem in the base welfare set, you're going to use the correct distribution lambda. But basically, once you have this small observation, you can decompose this problem further and write it as a problem. This is an observation in Alonso and Camara that you can write the heterogeneous priors model by, again, playing with the objective function as a problem where the sender and the receiver have the same belief, mu naught, but we play with the utility function of the sender. So we're going to have now an indirect utility function that combines the beliefs of the planner and the beliefs of the outside observer. But basically this problem over here, sort of, I will say we quote unquote know how to solve. This is an instance of the standard Bayesian persuasion model. But this observation basically says that a welfare profile is in the Pareto frontier if and only if I can find a belief lambda such that W is or a direction lambda, such that W is a profile induced by the information structure that solves this particular problem. And for us, and of course, the base welfare set is convex. This extends to all the boundary profiles. And we see this as a complementary characterization of theorem 1, because basically theorem 1 gives you the convex hull of theorem 1 characterizes a set via the convex hull of the graph of a vector valued function. And you might think, I'm not going to do that in a particular application. And actually, when we solve the examples in the paper, we use theorem 2, because theorem 2 allows you to recover the whole boundary of a convex set via real valued, in a sense, Bayesian persuasion problems. But we still think that both characterizations are complementary, because there's many instances, think about solving Nash bargaining, where you're not going to have a social welfare function that is clearly expressed in terms of Pareto weights. Of course, Nash bargaining, eventually, endogenously, you will have some Pareto weights, such that if you were solving the maximization with those Pareto weights, you will recover the same as Nash bargaining. But many times it's hard to determine which weights these are. And therefore, we think of, like, depending on the application, you might rely on theorem 1 or theorem 2. And with this, I will use now, can I see the sidebar? No. Okay, so I will, unfortunately, flip a lot of slides to get to the conclusions, because now I am officially out of time. So basically, the goal of the paper is to provide a framework to evaluate the welfare implications of information policies. And we do this in maybe a very econy way, in which we're describing everything that is feasible and the welfare trade-offs implied by choosing amongst different information structures, with the goal that then it is the social planner or the policymaker that has their goals and uses them to pick something out of the sets, and therefore, by implication, an information structure. And we think of this as a unifying tool to evaluate in the same language the welfare implications of different information policies, without having to take a stance on what your particular objective is. And we have many things in the to-do list, but with this, I'll just conclude and say thank you for your attention and your questions.
Thank you very much.
Thanks.
Questions, remarks? So I don't see. Please go ahead if you have questions. And not then. So you mentioned in point 1 in the future directions that, and more generally, moral hazard. So sorry. So what do you have in mind in this?
Okay. So social score design is like using information to induce certain actions, a little bit like what the Chinese government is doing. But that is that is one potential version of moral hazard. But you could imagine another way in which you could think of moral hazard, which is just determining not only determining the distribution of types in the that sentence is very obscure. So the reason for the more general is you could think that in our model we have all the agents in the prior is exogenous, and you could think of this as everyone in the population has to participate in the mechanism. But you could imagine settings where what information structure you're going to choose determines participation, and therefore determines the prior. So you're jointly determining who the feasible set of posterior distributions that you can induce when you're moving the information structure.
So endogenizing the
Yes,
prior.
endogenizing the prior. Yes.
I see. Thank you.
Yes, that's a way better. That's how the slides should be.
I learned it from
Thank
you
you.
for sure.
No. This is very useful.
Further questions? Too many shy guys in the audience for sure. So then thank you very much again.
Thank you. Thank you for having me.